Hey guys, here we go again. Another 2026 bio problem. This time it's the Ratsnare. So this is the problem. Once again, that's not the right thing. Feel free to pause and read it, but I'm going to explain it to you myself. So in this problem, we have a bunch of seats in a row equally spaced. So let's say we have 7 seats in this case, and we have a bunch of actors who have to sit in these seats. And the actors have names that are letters, so A, B, C, D, E, F, G in this case. And we have to seat these actors in these seats, and they sit down according to certain rules. And so each one always sits in the seat that is furthest away from all existing actors so far. So A always sits in the first seat, and then from then on, each one sits in the seat that is furthest from all the ones so far. So B will sit here because B wants to sit as far away from A as possible. Then C will sit in the middle, and so on. So by the furthest distance, I mean the furthest minimum distance. So each actor tries to maximize the distance to its closest other existing seated person. So if we take a slightly smaller example, just with 5 seats, this is the one given in the statement. Then A will sit here, B will sit here, C will sit in the middle, because now the distance is 2 to any other person. If C sat either here or here, then the distance would be, if C sat here, for example, then it would be 1, so that's worse. So C sits in the middle, so now the distance to the closest one is maximal. And then D has 2 options here that are equally bad, because they're both right next to another person. So D will choose either of these. Both of these choices are fine. So either D will sit here, which means E will sit here, or A, B, C, D will sit here, and E will sit here. So there are 2 seating options for n equals 5 people. There are 2 options, these 2 options. Those are the 2 options for 5 people. So this is the setup of the problem. This is informally known as the urinal problem as well. But that joke has been made. But what does the problem ask you? It says, so given an n, a number of people, imagine all these possible valid seating arrangements for that n. So in the case of 5, there are only 2 of these. And then imagine writing these all out as strings. So this first one is A, D, C, E, B, and the second one is A, E, C, D, B. Those are just strings, right? And imagine sorting those strings lexicographically. So just sort them alphabetically, basically, as they would appear in a dictionary. And then you're also given a position P. Let's say in this case it's 2. And you have to find the pth entry in that list, in that sorted list. So in this case, the second of these in sorted order is this one. So the answer would be A, E, C, D, B. So that's the problem. If you sorted all of these, which one would be, give us the pth one? So that is the problem. And if you also look at the problem, you'll see that the possible values of n are quite interesting. If you look at this, they're a strange set of values, but we'll come back to that. But you can start thinking about that as to why that is. So this is the problem. The first thing that might now let's begin the solution. But the first thing that might come to mind here is that if you've done any British Informatics Olympiad round 1 practice, or any of those rounds in the past, you'll recognize that this problem fits into a specific pattern that often many round 1 problem 3 problems have, which is that it's asking you to find the pth lexicographic string out of some set, and this is fairly common as a question 3 in round 1. Now, this being a round 2 problem, it's slightly harder than most of those, but you can still take one of those typical, the typical strategy that you usually use for those problems, which is one of the ways you can go about those problems is if you want to find, let's say, so you want to find the pth string that satisfies some category, that fits into some category, lexicographically. If you're able to answer the following question, how many such strings that I care about start with a certain prefix, then you can solve this problem. And how do you do that? Well, you just say, okay, so I'm going to have to fix this string. I'm going to have to find this whole string letter by letter, right? I'm going to have to find it letter by letter. And so let's try the first. Let's just find it one by one from left to right. So let's find out what the first letter is. So first of all, let's find out how many of these strings start with the letter A. And in this case, for this actual problem, there's two strings that start with the letter A, right? And so we compare that to P, and we say we have 2 strings starting with A. If the index of the string that we're looking for, which is P, is bigger than this number, then the string we're looking for doesn't start with A. It starts with a bigger letter. If it's less, then it does start with A. So if the index of the string we were looking for is 1, then we'd say, okay, we've got 2 starting with A, so it must start with A. So now we just want the first string that starts with A. So we just move on to the next letter. Rather than just looking for the first string, now we know we're looking for the first string that starts with A. If we instead had a 0 here, if we thought 0 strings start with A, then we'd move on to B as the next letter. But so we know 2 strings start with A. If we were looking for the third string in theory, for example, or let's say we were looking for the 7th string, so P equals 7. I know in this case there are only 2, but let's imagine there were more. And we know that there are 2 strings starting with A. Well, we know that the 7th string won't start with A if there are only 2 starting with A, because A is the first, again, in lexicographic order. So this means we'll have to move on to B as our next option. Let's try B. But now we're no longer looking for the 7th string, right? Because we've already discarded 2. We know there are 2 smaller strings in alphabetical or lexicographic order. We know there are 2 smaller strings starting with A that we've already discarded. So now from now on, we're looking for the 5th smallest string because we've discarded 2 starting with A. And so this is how you repeat. So if there were now 2 more starting with B, that's still too small, but so we'd move on to C. But now we're only looking for the 3rd string starting with C or above. And now maybe none of them start with C, so we'd still keep this as 3, but move on to the letter D. And then finally, if we have 5 strings starting with the letter D, now we're only looking for the third one starting with D, and so we'd fix that, and then we'd move on to the next letter. Now we're looking for the 3rd string starting with D. And then we repeat the same thing, like DA, how many strings start with DA, and so on. So we can do this quite reasonably quickly and efficiently if we can answer this question. For any prefix, how many strings that we care about in this set start with that prefix? So that's the typical way you'd go about this type of problem. But now, how do we do that in this case? Because this problem seems like it's a trickier situation, right? Because these seating arrangements, like, how do you answer this question? How many seating arrangements are there that start with D? I mean, DA is obviously 0 because we know that in this problem, all of them start with A. But if we had, say, A, E, C, or something, like, how do you answer this question? How many strings start with this prefix? So to do that, we're going to have to take a bit of a closer look at just what happens in this problem and how these people end up sitting down. We need to understand that a bit better. So let's take one of the lengths that's given in the one of the values of n that's given in the problem, which is 7, and just take a look at what happens. So we've already looked at 5, and the 5 case is quite simple, but we want to care about a slightly bigger case. So what happens with 7? Right, we've got A will always sit at the front once again, and then B will sit at the end, and then C will sit in the middle. So if the number is odd, C will actually always sit in the middle. And now we've got two gaps of size 2 left. And where can D sit? D can actually choose any of these positions because they're all equally bad. They're all right next to someone. So D can choose any of these positions. And whichever one D chooses, if you look at it now, where will E sit? It's still any of these positions because they're all still equally bad because their closest distance to any other person is 1. So now that you've reached this situation, from now on, wherever every person sits, all the remaining positions are still equally bad. They're all right next to someone. So actually, D, E, F, and G now can sit in any possible arrangement. Like this is fine. E, F, G, D like this is fine. They're all fine. So actually for 7, we have A, B, and C sitting like this. And then these 4 spots are D, E, F, G in any order. And so this quite nicely describes what kind of seating arrangements are possible in this problem for n equals 7. So we can solve this now for 7. It seems not too hard because we can very easily tell whether a seating arrangement is valid or not. It just has to be A, B, and C have to be in these fixed positions, and then D, F, G can be wherever you want. Okay, so 7 is nice. N equals 7. Let's move on to something bigger. Let's move on to n equals. So we want to n equals 8 maybe. 2, 3, 4, 5, 6, 7, 8. We have A here, B here, and then C can now go in 2 possible places, right? C can go in 2 possible places. And now depending on where C goes, let's say C goes here, right, in the one on the left, then D will go here, right? D will go here because this is now the only remaining spot that's 2 away from everyone else. And then E, F, G, H will go anywhere you want. And so D will go in this position, and then the others can go anywhere you want again because now everyone's next to someone, directly next to someone. But so now it's getting a bit weird because if C had taken this spot, then D could sit here and not here. But now that if C takes this spot, then D can sit here and not there. So where D can sit is affected by what spot C takes, and this isn't the same set of spots that gets taken up. So n equals 8 starts to get quite complex, actually, if you think about it. And the reason this kind of happened is because the n is even, so C could sit in 2 different spots next to each other, and that just changed the outcome of the whole remaining seating plan. But if you go back to the problem, you actually see that n equals 8 is not one of the input values for n. So 8 is not one of the input values, and actually if you look at it more specifically, none of the larger n's are even. So you're starting to notice something is going on in this problem. There's something happening. So n equals 8 is just not, it's not in the problem. So we can look at 9, which is in the problem. So B goes at the end, C goes in the middle because it's odd. And now what happens? Now D can take any of these 2 spots because they're the furthest from everything else. And then E will take the other one. Whichever one D takes, E will take the other one for sure. And then we've got these 4 spots, and then F, G, H, and I will take those 4 spots in some order. So if I now give you F, G, H, and I, I'll just write them in this order, but they can take any of these blue spots in any order. So this, if you look at this looks a lot simpler than the n equals 8 situation, because once again, like the 7 situation, the n equals 9 setup has, all it has is so A, B, and C are fixed, and then we have D and E, which take these 2 spots in any order, and then F, G, H, and I, which take these 4 spots in any order. So we've just got groups of these letters that take groups of spots, groups of chairs, and each of those groups can be rearranged, commuted in any order, and the groups also don't affect each other. Like where D sits, whether D takes this spot or this spot, which of these 2 spots D takes, does not affect where F, G, H, and I can sit at all. So these are kind of independent, which makes the problem a lot easier. Right? Because if we think back to what we're actually planning to do with these seats, we want to be able to answer the question: how many seats are there starting with this prefix? How many arrangements are there, seating arrangements starting with a certain prefix? And so if we get a certain prefix like this, A, B, C, A, B, D, F, or something, right? Or A, like this one we obviously know doesn't work because B is in the wrong spot. But let's say it looks more like this, it looks more realistic. Still, we can check whether these letters are all in their valid sets, because we know that these 4 blue seats that I've marked in blue have to contain F, G, H, and I in some order. And in this case, yes, G and F are in those seats, so that's fine. But if this G, for example, was an E, E can't be here. These seats are reserved for F, G, H, and I in some order. So E here would mean that there are 0 starting with this prefix. But now that we have G here, this is fine, and then these two seats we know are for D and E in some order. And then this is also fine because D is here. So now we know this prefix is valid as a start. And now the rest is just combinatorics, because we just know that there are 2 blue seats left to be filled, 8 for H and I in this case. So there are 2 blue seats left to be filled, and those 2 can be filled in any order. And then this has to be C, and then this has to be B, and this has to be E. So there's one of these seats for D and E, one of these DE seats left to be filled, and there's only E left to fill it. So the rest is just combinatorics. So the fact that what we said happens is that we just have groups of seats and groups of letters to fill them, and they're independent, just makes this easier, right? And we'll actually notice that the same applies for the larger cases that we've got in this problem. So it applies to all of these, actually, even the small even ones. And so if you look at n equals 4, we've got 4 spots, A, B, and now C and D can go in these 2 spots in either order. And so in this case, we just have, if we number these positions as 1, 2, 3, and 4, position 1 has to contain A, 2, position 2 and, well, let's just say position 4 has to contain B, and positions 2 and 3 have to contain C and D in some order. So it's still satisfied. Oh, you can't see what I'm writing. Okay. So I drew this, n equals 4, A and B, and then C and D have to take the middle 2 spots. And then position 1 has to be A, 4, B, and then 2, 3, C and D in some order. So this still satisfies the same kind of arrangement we had up here, where we had just sets with just bijections between sets, basically. And yeah, that's what happens. And so these ends in the input are all nice in the sense that they're all either small enough like this that they only have, let's say 2 spots, or they're odd. So the annoying situation is a large even number. That's the annoying situation. So, or they're odd. Let's say in the case of 9, 1, 2, 3, 4, 5, 6, 7, 8, 9 is odd. And then if you subtract 2, the A and B just always get subtracted off the sides. So the rest, the 7 remaining, is still odd, but then if you take the middle seat and split it in half, it stays odd. And then again, if you take the middle seats in each one and split it in half, they stay odd. And that's what gives us this property, which is why we don't have in the input, say, the number 11, because the number 11 wouldn't have this property, because these wouldn't be 3s, they'd be 4s on each side, and that would be annoying. But so all these ends in the input are nice, and you can draw these all out if you want and test this theory. I can draw 25 for you. Okay, so even for 25, I've drawn out the bulk of the case here. But so for 25, we start off with, again, A, B, C in the middle because it's odd. And then the two sides that we split into are both of size 11, the two gaps. And then, because again, they're both odd, they both have one unique middle spot. And then those two are taken up by D and E in some order. So position 7 and 19 will be D and E in some order. And then the next one, let's use red here. The next ones, and we now have 4 gaps of size 5. And so, again, these are odd. So this is why 25 is a nice number. So the middle ones positions in each of these will be taken up by F, G, H, and I. So that'll be 4, and I'll just write them in increasing order. But once again, these can be filled in any order by the red letters. F, G, H, and I will go in these positions. So we've got 4, 10, 16, and 22 for F, G, H, I. And then finally, we are left with gaps of size 2, a bunch of them, 8 of them. And then this means that every position here is just all the same, so that the rest of the letters can take any position each. So the letters from J, K, L, all the way through to Y, which is the 25th letter of the alphabet, will be in these positions. So the positions 2, 3, 5, 6, so on to 24 will be J, K, L through to Y. So those will be the positions that I haven't filled in here. The remaining positions, all the other ones. But so now you can see that 25 also satisfies this, and so these numbers, all the numbers in the input possible out of these are like this, in that they if you take n minus 2, so let's say 25. If you take 25 minus 2, that takes off the A and B on either side. You're left with 23, and 23 is a number which is odd. And if you subtract 1, divide by 2, so take out the middle spot, and divide by 2, you're left with 11, which is still odd. And again, if you subtract 1, divide by 2, you're left with 5, which is still odd, and so on. You get down to 2. So any number like this, which can be which you can reach starting from either 1 or 2, and applying the operation like times 2 plus 1 as many times as you want, and then adding 2 at the end for the A and B is a nice number for this problem, because you have this property. And so that just means we've basically just solved this problem, right? Because we now know that every one of these ends can be decomposed in this way. And so, for example, for 25, what would you do? To answer a query of the form, how many strings start with a certain prefix, all you need to do is, so let's say you have a certain string, right? A L, J, I, something like this. Okay. Something like this. I should have just made this shorter. Okay, let's do this. So for this string, this we just have to check for each letter if it's in a position that corresponds to the set of positions that it can be in. So this A is correctly in its position. L and J can be in positions 2 and 3, so that's fine. Can I be in position 4? Yes, it can, so that's also fine. 5 and 6, E and Y. Y can be in 6, but E and 5, this is incompatible actually. So E has to be in one of these two. So position 5 contains letters from J onwards. So actually, there are 0 strings starting with this prefix. So that's how you check whether there are 0 strings or not. And then otherwise, if this E was something else, let's say this E was a Q, then this would be okay. Let's actually just change this D to an E. So this is okay, for example. So there is at least one prefix starting with, at least one string starting with this prefix. And then to count how many there are, it's just combinatorics. Because we have these sets, right? And so the first set is of size 1, the second set is also of size 1, the third set is of size 1, this set is of size 2, 4, and then 16. So we have all of these sets, and then from each one, we've already used up some values. So we've used up the A, for example, so we have 0 of these left. We haven't used up the B or the C. I mean, these are really the important ones. So from the 2, we've already had this spot, the 7, filled. We've got 1 left. From the 4, these are the red ones. We've already filled one of the spots with I. So we have 3 left. And from the 16, these are the gray ones. We've already filled 4 of the spots. So this is 12, right? So we now just have to find the number of ways of filling the remaining slots. And so we have the group with 12, for example. There are 12 factorial ways of filling those into the remaining 12 gray slots. And there are 3 factorial ways of filling the remaining red ones into the 3 remaining red spots, these 3, times 3 factorial, and then times 1 factorial time for there's only one way of placing D here because we've already placed E in spot 7, times 1 factorial, and then, I mean, I guess for completeness we can do 1 factorial, and 0 factorial for C, B, and A, but, you don't have to include this, but for completeness I will. So 1 factorial times 0 factorial. And so this is the number, and this will be however many strings there are starting with this prefix. So now we just know how to compute this for any prefix. And this is nice. We've solved the problem. We're just going to do this and incrementally update the string in the same way, the way I explained at the start of the video. And you'll actually, one cool thing that you'll notice here is that the number of strings that start with a certain prefix here doesn't actually depend on the prefix, other than just to make sure that it's a valid prefix. So once you've checked that a prefix doesn't have any wrong letters in the wrong places, so once you've checked that a prefix is a valid prefix, and there's at least one string starting with that prefix, you don't actually need to. You can just stop caring about the letters. The number of strings starting with this prefix is now just a function of the length of the prefix. So that's quite cool. Anyway, so this is how you solve the problem. When you actually go about implementing this, you can just keep track of this number that I had written out here. Since I said it's literally just a function of the length, you can just store what it is. So initially you can just store the whole thing, which would be, so for the empty prefix, there are 16 factorial times 4 factorial times 2 factorial. So if we hadn't subtracted anything from any of these, times, well, these 1 factorials don't matter, but there are this many strings for the empty prefix. So there are this many strings in total. So you can start by having this number in your stored in memory, and then each time you try a letter, you see, is this a valid prefix? If it is, then we already have the number computed of how many there are of that prefix. And then each time you move on to the next letter, you just take this this number and divide it by. So let's say we were moving from this prefix now to the next one, we would be fixing also, we would be starting to fix this letter. So if we realize that E is the correct letter here, then maybe we're going to start with, we start with A again. That obviously doesn't work because we've already used A and this is the wrong place for A. So B also doesn't work because this is the wrong place, but we're going to move on and we're going to get to J is also a duplicate. K is going to be the first one that we try for position 8. And so now we're trying this. And instead of whatever we had here for 12 factorial times 3 factorial times so on, we now want to, we're now using this K, so this 12 factorial is just going to become an 11 factorial. And so we can, if we already have this number stored, then we can just divide by 12 and decrement whatever variable is storing the number remaining. So the 12 will drop to an 11. You can just, again, you don't need to really optimize and do this, but it's just easier to store it this way. But you can just, like the time complexity does allow you to just go through all 25 letters each time you do this. But this is fine. So yeah, that's the solution to Ratsnare, the Ratsnare. And one more implementation detail, you can choose to do casework here on N in the implementation. The implementation I provide in the description, which is my code, I don't actually do any casework on N. I just go through this process of dividing N into, like, choosing the middle odd part and then dividing it into sets and so on. And so I just automate the process of dividing the N positions into these sets of positions and letters, and then just work on it automatically from there. You can also do this by hand, because if you just hard-coded the cases for just all of these N, it honestly might just be quicker to write them all down by hand rather than writing that code. Up to you. But that's the way I did it. And final note for this constraint, actually, you might be thinking that this P is too high, actually. So the largest P that you could have in the input actually is this number, because this is the total number. We just figured out this is the total number of strings for N equals 25, and that's the biggest one, the one with the largest value. And this number comes out to, well, something that isn't up to 2 to the 63. I don't remember how big this number is, but it's a few orders of magnitude smaller. So it's more like 2 to the 50, I think. Yeah, so that's that. If you are interested, you can also try solving this problem. You can also try solving this problem for the different values of N that aren't so nice. So let's say 24 and all of the other values that don't have that property that we've discussed. So feel free to try that if you'd like, as a challenge. But I'm not going to go through that here. That's it for this video. Once again, the code is in the description if you'd like to take a look. And the other videos for the other solutions, for the other problems, from this contest will also be linked in the description.